Okay, the Chapter 3 sample test for Calc 172. Find the critical points and use a second derivative test to see if they're maximum or minimums or neither. So we're going to find the critical points, we got to take the derivative and set it equal to 0. So f prime of x will be, so if I bring the 3 down, it'll be, the 3's will cancel and I'll get 2x squared. The 2 will come down and cancel the 2 plus 3x, and the derivative of negative 5x is negative 5. That looks like it might factor. 2x and x and minus 5, let's see, to get 3, I'll probably put the 5 here, so that'd be 5x and 2 times 1. One of these has to be minus, I believe it's the minus 1, so minus 2x plus 5x will give a 3x in the middle. So this equals 0 when x is equal to negative 5 halves. Just set that equal to 0 and I get that. Setting that equal to 0, I get x equal 1. Those are the critical points. Now I need to know whether they're max or min or neither. So I'm going to take and find the second derivative, and that would be 4x plus 3. Now, I'm going to put the negative 5 halves in and check the curvature. So f double prime of negative 5 halves is 4 times negative 5 halves plus 3. So that becomes negative 10 plus 3, negative 7. So it's concaved down. So that means we have a max at that critical point. And now we're going to do it at 1. So we're going to, the f double prime of 1 is going to be 4 times 1, or 4, plus 3, which is 7. So that's positive, so it's concaved up, which tells me it's a minimum at 1. Now, this is a cubic with a positive leading coefficient, so cubics look like that. So it makes sense that the one on the negative value is a max, and the one at 1 is a minimum. And you could have graphed this and saw that, but I want you to show the calculus that shows that. Find the absolute max and absolute minimum on the interval from minus 1 to 1 for this. Again, you could graph and probably get this, but I want you to do the calculus techniques. So we're going to find the derivative. So the derivative of the inside is pi over 2, because pi over 2 times x is just pi over 2, and times the bigger picture, which is 4, the derivative of sine is cosine of pi over 2x, minus the derivative of x, which is 1. And we're supposed to set this equal to 0. So that means if I set that equal to 0, I'm going to get divide both sides, or subtract or add 1 and then divide by that. So I'm going to get cosine of pi over 2x equal to 1 over see, 4 times that, that's 2 pi. And so then I need to know when cosine of x is equal to this. So I'm going to go 1 divided by parenthesis 2 pi, and I get 0.1592-ish rounded pi over 2x. So now I have to get rid of the cosine. I got to go cosine inverse of 0.1, well, that answer. And I get, let's see, make sure my mode is in radians. Yep. So I get pi over 2x has to be 1.41 plus, let's see, the cosine equaling to some number. The cosine would be 0.15, would be somewhere up here, which is almost pi over 2, 1.4 radians, and also down here. So there's a couple of places that happens. And then I have to multiply both sides by 2 over pi. It happens at plus or minus this angle, so I get x equals, and then there's multiples also, but I'm just going to get these two because I'm between -1 and 1. And neither of these answer, let's see what the answers are. 1.41 times 2 divided by pi is 0.89 plus or minus. So those are both inside that interval. So I need to now see if the height at each of these places and at the endpoints to find out where my absolute max and absolute min are. So I'm going to type this into y equals 4 sine of pi x divided by 2 minus x. And second table set, and I'm going to put in 0.897 and negative 0.897 and -1 and 1. So what are my absolute and max and mins? Well, my absolute max looks like it's the 3.05. Absolute max 3.05. Happens at the positive one of these answers, positive critical point, 0.897. And my absolute min happens at the negative 0.897, and it happens to be 3.051 negative. This 5.1 positive. So there's my absolute max and mins. Find the inflection points for this. Inflection points are when the second derivative is equal to 0. Then determine the intervals where it's curved up. And so, first of all, we got to take the derivative. And this is a product. So f prime of x is going to be the derivative of the first times the second plus the derivative of the second times the first, which they both have e to the x, so I get 1 plus x times e to the x. That's the derivative. But to find inflection points, I got to find the second derivative. So f double prime of x would be the derivative of this times that plus the derivative of that times this. And there's an e to the x in both of these, so I get 1 plus 1 plus x, so that's 2 plus x times e to the x. And this, the second derivative, is what I want to set equal to 0. Well, the only way this equals 0, this is never 0, so it only happens at x equal -2. That's where the inflection point is. And to see if it's concaved up or down before that, because it's going to be all of one on one side and all the other on the other side. So I'm going to put something smaller than -2. So I'm going to try x equal -3. So that's between -infinity and -2 to see whether it's concaved up or down. So I'm going to put -3 in here. And I get 2 plus a -3 is -1 times something that's always positive. So I get negative times a positive, a negative. So f double prime at -3 is less than 0, which means it's concave down. So probably it's concaved up on the other side, but we'll check something on the other side of -2, like -1 or 0. So let's just find out f double prime as 0. That should be easy to work out. And so 2 plus 0 is 2 times e to the 0 is 1. So this is 2. That's positive, so it's concaved up above here. So when is this curved up? It's curved up from -2 to infinity. I started to say including the -2, but that's where it changes curvature. So you can't do that. It's just from -2 on up, it's curved up. Okay. F is decreasing. Okay, so this graph. Match the description of f with the graph of the derivative shown. So these are derivatives. So you got to think derivative. So this graph is always positive, and the derivative tells the slope. So the slope of f is always positive. It's really a big positive, so it's a steep slope getting to be less steep, but still going. So f is increasing because it's positive slope, and it gets less and less steep, so it's got to be concaved down. So this is D. Here, the slope is the value of the derivative is always positive. It's above the x-axis, so it's positive, so it's always increasing. It's increasing a little bit, gets a higher, steeper slope, and then it gets less. So it's f must go not very steep, getting steeper, and then getting less steep. Steepest here, and then get less steep. So it's increasing, concaved up, and then down. So this is F. This one, always positive slope, so because it's always above the x-axis, so it's always increasing slowly and then more. So it's increasing slowly, then more. That makes it's increasing slowly, and then it gets steeper. So that makes it concaved up. Increasing and concaved up. C. Okay, so these lines up here are supposed to line up with numbers. They were supposed to. So we're supposed to draw a curve that has a negative first derivative and a positive second derivative, positive first derivative, positive second derivative, negative first derivative, positive, and we'll try to do it all the way through. So kind of imagine a graph grid down here, and it doesn't matter where we start, but it has to be, see, this is a slope, so it has a negative slope, but it's curved up. So it's curved up with a negative slope. So it could be anywhere curved up with a negative slope. After -3, it has a positive slope. So it must have a zero slope at -3. So it must go to a positive slope, still concaved up, all the way to here. Now it could have been there, could have been, or it could be down lower, but it's concaved up, going down, going up. Negative slope, positive slope. Now we have a negative slope again. Well, if I'm going up and then all of a sudden I'm going down, I'm going to have a cusp and curved up. So concaved up. And then it goes to increasing and concaved up. And then it goes to increasing and concave down. So note that the table lines line up the graphs of -3, 0, 3, and 5. So this is what the graph would look like with a cusp there. It would have to be something like this. Number 6. A rectangular sheet of metal is made into an open top box by cutting equivalent squares out of the corner. The sheet of metal is 3 feet by 6 feet. Cutting squares out of each corner. Then we're going to fold them up. The squares are all the same size. And so this will fold up. This piece is gone. This folds up. And this is gone. This folds up. This is gone. Determine the dimensions of the box that would have a maximum value. Well, we don't know how big to cut that, but they're squares. So the volume of the box will be the width of the base. Well, that's 3 feet minus x and minus x minus 2x. That's this length. This length is 6 minus 2x. And the height of the box will be, this flap folds up and often are all going to be x high. That's the volume. And if we're going to maximize, we're going to find the derivative of this. And we could do the product rule on this, triple product rule, or we can multiply this out. 3 times 6, 18, minus 6x minus 12x plus 4x squared, and all that's times x. So I get 4x to the third minus 18x squared plus 18x is the volume. So I want the volume's derivative, dv dx. So that's 12x squared minus 36x plus 18. And I want to set this equal to 0. Looks like I can divide everything by 6. 2x squared minus 6x plus 3. I might be able to factor that. Let's see, 2x and x and 2 times 3, 1 times x. That's not going to be 6. 3 and 1. Oh, not going to get it factored. All right, so I'm going to do the quadratic formula. The negative of b, a negative 6 is 6 plus or minus the square root of b squared minus 4 times that's 8 times 3 is 24 over 2a. So 36 minus 24 is 12. So I get 6 plus or minus the square root of 12 over 4. If I want the decimal approximations, I'm going to get 6 plus the square root of 12 divided by 4. One possible answer is 2.366. The other possible answer is 6 minus the square root of 12 divided by 4, which is 0.634 feet. And then I got to check and see if it's reasonable. Could I cut a 2.33 foot square out of this corner and this square? If it's only 3 feet long, the biggest I could do is 1.5. That's not a reasonable answer. So the dimensions that work would be 3 minus 2 times that. So let's double that. Times 2 is 1.26. 3 minus 1.26 is 1.73 inches by 6 minus 1.26 is 4.73 inches, and x is 0.634, feet. Feet and feet. There's the dimensions. This by that. 500 meters of fencing are going to use to make 2 equivalent corrals. Use calculus using calculus to find the dimensions if the area enclosed is maximum. It doesn't say define the dimensions, but that's what I wanted you to do. So if we call this x and x and x, we can call this y and y and y and y. And we got to use the fencing to make these. So 3x lengths plus 4y lengths uses up to 500 meters. So that's my constraint. I got that much fencing. And I want the area. Let's see, the area would be x times 2y, but that's two variables. So I'm going to solve for, say, y in this. Y would be equal to 500 minus the 3x, and then divided by the 4 that's in front of the y. So the area then becomes x times 2 times this. 2 times this, 500 minus 3x over 4. Well, this 2 would reduce this to a 2, and this x could multiply in, or I can divide the 2 into both of these. So I'm going to have x times 250 minus 1.5x, which is 250x minus 1.5x squared. That's the area. So the derivative is 250 minus 3x. If I set that equal to 0, x is going to equal 250 divided by 3, which is 83 1/3 feet. Meters, 83 1/3 meters for x. And I'm going to use that 3 times, and I'm going to get, that'll be the 250, and there'll be 250 meters left for those. So the y is going to be, see, 3 times this is 250. 500 minus 250 leaves 250 for the y's, divided by 4. Y is 250 divided by 4, which is 62.5. 250 divided by 4. 62.5 meters. And those are the dimensions of the pens. The x's are this, and the y's are that. And the last page. A spherical balloon is being inflated, and the radius is increasing by this rate. So dr dt is 1 centimeter per second. So what is the rate in the change of the surface area? Oh my goodness. When the radius is 7. So the volume is 4/3 pi r cubed. And the radius is changing at this rate. The surface area is this formula. And so the rate of change of it, if I take the derivative with respect to time, the change in the area with respect to time is 4 pi times 2r d, the change in the radius with respect to time. And we know that is 1 centimeter per second. And we're supposed to figure this out when the radius is 7. So we're going to put 7 in there. And the change in the area with respect to time, looks like we didn't need this formula, is 4 pi times 2 times 7 centimeters times this, which is 1 centimeter per second. And we get the change in area, which should be centimeters squared per time, which is second. So we're going to get 4 times 2 times 7, 56 pi centimeters squared per second. Or if you want, in decimal, 175.9293 centimeters squared every second is how fast the surface area is increasing if the radius is increasing by 1 centimeter per second and the radius is already 7 centimeters. Okay, this one's a little tricky to read. So a fighter jet is flying at 800 miles per hour at an altitude of 5 miles. So here's the ground, and up here is our fighter jet. I should make it more like a jet. And it's flying at 800 miles per hour. And it's at an altitude of 5 miles. It passes over the head of an observer standing on the ground, so it's right over the head of an observer. At what rate is the angle of elevation changing when the jet is 13 miles from the observer? So it passes over, and eventually it's 13 miles down here. And the angle of elevation is this angle, how much you have to elevate your view, which is going to be same as this because that's alternating interior angle. So this angle, which is the same as this. We want to know how that angle is changing with respect to time. Well, let's see. This angle, this side is always 5. It's flying at 5 miles high. This side is changing, so I got to put X there. And this side is changing. I could put a Y there. I have a right triangle, and I could do Pythagorean theorem. 5 squared plus x squared equals y squared. But I want to involve the angle. And I know this the rate of change in this side, so I'm going to try to involve the angle with these two sides. One I know and one I know something about. And see, and that's opposite and adjacent. So the tangent of theta is 5 opposite over x. So now I finally got a relationship between theta and the direction the plane is flying. I'm going to take the derivative of this. See, that's same as 5 times x to the minus 1. I'm going to take the derivative of this respect to time. Let's see, the derivative of tangent is secant squared. But the angle is not time, so I have to go times d theta dt, this derivative of the inside, equals, now I got to take the derivative of this with respect to time. Well, the derivative of this would be minus 1 times 5, or minus 5 x to the minus 2. And since I'm doing it with respect to time, and this is x, I have to go times dx dt. How fast is the x changing? Well, it's changing at 800 miles per hour. What is x? Well, x is when it's at 13 miles. So I got to put 13 13 there. I got to put 800 miles per hour there. And what's the angle when it's at 13? So I have to go find the angle that has 5/13 as the tangent. So I got to go tangent inverse of 5 divided by 13. Let's do a 5 instead of a 3. And I get the theta is 0.3671. So I have the angle. Actually, I just need the secant. And so to get the secant, that's secant's the reciprocal of cosine. Cosine is 13 over y, so the secant's y over 13. So I can get the secant without doing this trig thing here. I can say 5 squared plus 13 squared square root gives me this side. So 5 squared plus 13 squared, and then take the square root. And this side is 13.928. So secant's 1 over the cosine, or the cosine is 13 over 13.92. So the secant is 13.928 divided by 13. This divided by 13 is the secant of the angle, and I got to square it. And so this number is 1.148 times what I want, how fast the angle of elevation changes, d theta dt equals, and this is -5 times 13 to the -2, which is that number. And I got to take it times 800. And so this comes out to be -23.669. So I got to divide this into there, divided by 1.148, and I get the change in the angle in terms of radians. It's losing 20.6 radians per hour. So this angle is getting smaller. This angle is getting smaller at a rate of 20.61 radians per hour. Because this was in miles per hour, the speed. Tricky one. Okay.